Hello everyone, NadLabs here. Today we're going to be doing something a little bit different. Today we're going to be extending the biggest array project in Godot, and this time it's version 3.2.2 stable, and essentially this was the code used in the video I'm about to show. And the reason I had to pre-record everything is because this second video actually took about 4 hours to make, and of course it was never declared anywhere, but I'm just going to say up front that Godot wins, and we can't actually get to the limits of the array, at least not in terms of practicality, because if something doesn't happen in about 4 hours on a computer, then I don't think it's going to happen very soon. Or at least we can extrapolate from the data we've gathered, we can make a mathematical conclusion, but we can't really get to a physical conclusion through actually making Godot admit that it ran out of memory like we saw last time in part 1 of this series. So I'm just going to play the video. And I just want to note a couple things. This computer I'm using has an i7 10th generation, I believe 6 cores, base speed of 2.6. It can go up to 4.5 gigahertz. It has 16 GB RAM, Intel Optane, I believe, SSD, and it has an RTX 2060. So this is the computer I decided to use to test the biggest array, and I'm just going to be quiet and you guys can watch this video. So this is about, and just one final note, this is about 4 hours of video condensed into about 2 minutes. Now that the clip is done, I'm going to address a couple comments. One is that of splitting my actions into chunks, and that's, I think, what I tried to do. At least I'm not the best at Godot, obviously, but I tried to split my actions into chunks by using a timer, and as well as making the file size, or at least the amount that we put in, a lot smaller. So I believe it was around 100,000 before, and then we found out that was going to take a very long time. And then we stopped everything. We tried again with a much larger number. Of course, Godot didn't respond for maybe 5, 6, 7 real life minutes. And then it would respond, the timer would go, and everything would repeat. And we got to around 400 megabytes. No, sorry, we got to around 330 megabytes. And you also have to remember that this 330 megabyte figure, or at least approximation, is also in the pool int array, which I was told to use. If you use the pool int array, it's actually designed to help store integers. And if we go to the documentation, and you can see that this array is specifically designed to hold integer values, optimize for memory usage, does not fragment the memory. And before we were just using a regular old array. Now we're using a pool int array. So you have to remember that 330 megabyte figure, although it's smaller than the 600 megabyte figure that we saw in the last video, this 300 megabyte actually holding a lot more numbers and a lot more number ones as compared to the previous file, which I have right here. And the file in the video is actually holding a lot more number ones as compared to this one, because this is just a regular old 625 megabyte file of just ones repeated. But that's a 300 megabyte file of ones repeated in a pool int array. So I just want to make that clear. Also, I was asked why didn't I open this file. Let me just get to it, sorry. Why didn't I open this file? And that's because if I try opening any note editor or notepad or whatever, VS Code, Notepad++, I just get Notepad to not respond, and it takes a very long time. Of course, you're not going to see this open. If it was going to open it, it would open on some sort of like high-end computer with like 64, 128 GB of RAM. Obviously, a Threadripper probably. We would need a much upgraded system to open this file. But I'm just saying, on this computer at least, I just get a not responding error, and I have no clue how long I have to wait. I waited maybe like 5-10 minutes, and nothing happened. So I'm just going to conclude based on that evidence that this file isn't going to open, and that's as far as I'm going to go with this. If anyone wants to try opening in a higher end PC, I'll make sure to upload this file to Google Drive or some cloud sharing service so you guys can try it out for yourself. If you want, leave a comment on this video if you want that. I'll be sure to make that happen. Otherwise, I'm not going to be uploading it because I just don't want to waste my time with that. And with that, I'm sorry to conclude that we actually can't get to the end of Godot. Let me just slow this down so I can see the actual final figure. It's about 332 megabytes of data. And remember, that's still in a pool int array. It's not in a regular old array. So this is probably holding a lot more information. Okay, so as you might have seen in that time lapse, I'm just going to go up to 20, and these are the real numbers, and these are the actual numbers from both experiments, and these are just live. Like I just did this experiment, as you saw. The file is right here, right over here. You can see that this was the file, this was the final digit, and of course I know as a scientist that 20 data points is nothing, it's garbage, but it's a step forward to figuring out how big can an array go. Comparing the regular versus the pool int array, we can see that there's a significant amount of data saved. About half of it is saved by using the pool int array as compared to using a regular array. Now this makes me wonder, if I do equals, and this is a little Excel tutorial, equals, click anywhere, and if you type in a mathematical function, you can see the actual number, drag down. So these are the reg divided by 2, just to name what I'm doing. So I'm actually comparing these two values to see how far off they are. So I mean, we could do a percentage difference. For a percentage difference, if you don't know the formula, it's the new value, which is this one, minus the old value, which is this one. Close the bracket, divide it by the old value again, and that's the percentage difference. And of course, we're going to be multiplying it by 100 just to give it a percentage sign. And we can see how far off. So it's about, oh wow, so it's about almost half. So the first one's a little bit weird, but the rest are like pretty much, it's a direct divided by 2 if you want to go from regular to pool int. So it is quite optimized for storing integers. We can clearly see this. And now we're going to be doing a direct comparison between these values and these values to get a mathematical relationship. You can see that this is the function, and I'm actually going to be seeing what happened, or at least where was the value. So I'm just going to be doing a direct comparison between the regular, as you can see there, Excel highlights the regular column with purple, which is the x-axis. Actually, I'll just... So we can see over here, regular values are the x-axis, pool int is the y-axis, and of course you can see it's about a half. This is the slope, right? Y equals mx plus b. So you can see this is the slope. It's actually pretty significant. It's about 0.5, and I'm going to hop into a graphing program, or actually, you know what, forget the graphing program. If I just grab my calculator, and if I type in the values of, what is it? I have to type in the value of 625000. Around 625 megabytes is where we stopped last time. So if I just plug that into my calculator, if I plug this value into my calculator, then we get about this value. Plugging in around 625 kilobytes into this formula over here with a very high r-squared value, which just means how close the trend line is to the points, we can see that 625 megabytes in the regular array is about 300 megabytes in the pool int array. And if you know, we surpassed that actually. We actually went to around 300. Let me just get the correct figure. Highest value is 335,938. So putting those numbers back in, 335,938. And we're trying to figure out this value over here. So if we just do simple mathematics, so if we plug in this value into the y spot, so we get 3. Based on our time limitations, the final value we could have gotten, assuming it's a linear relationship between these, and we kind of proved it was almost linear, we can see that we got around 670 megabytes, sorry. That's the value we could have gotten in a regular array if Godot could exceed its 625 megabyte limit. So now the question is, what happens if we plug in this value for the y value? So let's just say, for the sake of hypothesizing and extrapolating, the pool int array finished at around 625 megabytes, right? Because this is these values are all in kilobytes. At least these values are in kilobytes. So let's say it finished at around 625 megabytes, and we're just going to do the exact same thing we did for this value. So the final value we get, assuming it's a linear relationship and assuming that the pool int array could have gone up to 625 megabytes, is we get this value right here. And that's a product of the mathematics, and we're assuming a linear relationship again. According to my final calculations, we get around a 1.18 GB file. So assuming I had more time with the beefy computer, the really spec'd up computer, we would have gotten around a 1.2 GB file in the regular array, but the pool int would have probably ended at around 625 megabytes. So I hope that satisfies some viewers and their quest of knowledge to know how far Godot will actually go. Okay, with that brings me to the end of this video, and I hope that satisfies some viewers. If we could get to the end of the pool int array, then we would have seen that the file size in a regular array would have been around 1.1 GB, and that's assuming a linear relationship. And that's all I have to say for this video. There might be a part 3. I'm not sure. I don't know what technology I can get my hands on, or if there be a new version of Godot, hopefully in the future, more memory efficient. I don't know what they'll do with the C++ code over there, but that's all I have to say for this tutorial. Have an amazing day.